for the fourth lab, which is about spring oscillating motion. So first I'm going to go ahead and share my screen. I'm going to share the tracker app. So now you can see. Here is the video we were given. So I'll play it and you can see that I've tracked the mass as it oscillates about for the 9-second video. There's many frames where it's oscillating, and as it is, there it goes, and I'll stop sharing that. I'm going to share my browser so you can see the GlowScript code. So here's the GlowScript code, so I'll just walk through it. So you got the mass of the ball, our initial, this is where the ball begins in that video, the position vector as well, and the initial velocity additionally. So here is gravity, obviously. This is the spring constant that was found, and the initial or relaxed length of the spring as well as L naught. Here I'm finding the current length of L for the video, and then I'm normalizing that to get the unit vector L hat, and subtracting magnitude L minus L naught to find S, which is the displacement.
And we're going to check out.
Here we're calculating all of the energy values for the system, so that's K potential, gravitational potential energy, K being kinetic energy, and spring potential energy as well.
And then the last weekend,
here is the time loop. So here we're just setting up some holding values for K, UG, US as well. The gravitational force, obviously, force of the spring here is calculated just like, so that's the spring constant times the displacement times that unit vector. And the net force is the combination of those two. Updating the velocity is simple. You just do the current ball's velocity add to it the net force divided by the ball's mass times delta t. And similarly for the ball's position, you take the current ball position and add the ball's velocity times delta t. And then here we're updating the spring values. Here I'm updating the energy values exactly the same way we did above. And then to find the change in kinetic energy or such, you just have to subtract that original value that was saved into these initial value holders. Now I'll run it.
This is for.
And I have to import a CSV file that was from Tracker that had the position.
Wait, how many nights are you spending in each
class? Yes, you can see it's oscillating.
The camper is almost rounds.
As you can see, oscillating similarly to the to the tracker data. Now I'll pull up, there's some questions for this lab. Is the energy principle satisfied? So yeah, the energy principle is satisfied because the change in energy, this delta E, is constant throughout. Even though these values change, the combination of them is always going to be equal to delta E, which is going to be constant. And that means that yes, the energy principle is satisfied. So as, say, delta K increases or delta U gravity increases, then something else is going to have to compensate, and that is true as delta E is constant. Another question. Using the data you obtained in Tracker, make two separate estimates of oscillation periods. First by estimating the period of oscillation from the X position data, and second from the Y position data. So here I'll stop sharing and I'll go back to Tracker so we can take a look at that. So from the X position data, it looks to be about 2 seconds approximately to get from this low point here to the next low point. So I would say 2 seconds. And then
How many
from
nights are you guys
the
there?
Y
Total.
position,
Everywhere.
The whole trip.
it seems to be, well, maybe more like 1.5 when you look at some, yeah, maybe 1.5 there, and
Okay.
about 1.5 here as well, as you can see.
Honestly.
So either way, I would say about 1.5 seconds to be the oscillation period. Thank you so much.